The next stop on our journey through classification algorithms in machine learning is the SVM algorithm, and that is an acronym for Support Vector Machines. And if that name sounds very weird or intimidating, do not worry. We are going to dive into exactly what each one of those elements represent in our definition and also in our case study. So, what does a SVM do? Well, the primary usage is for recognition. Now, that may seem a little bit over the top because anything that is in the world of classification really has to deal with recognition in some form or another. However, SVMs are very good at many different types of recognition, and that is the reason why I've listed that as the primary usage. However, many of the different classification algorithms could also be lumped inside of this category. Now let's dive into the definition. The definition of a SVM algorithm is that it is a support vector machine and it is a discriminative classifier formally defined by a separating hyperplane. In other words, given labeled training data, which every kind of supervised algorithm needs to have, the algorithm outputs an optimal hyperplane in which it categorizes new examples. Wow, that had way too many big words. So let's actually rip that apart a little bit and dive into what it means. Specifically, the elements we're going to pull out are discriminant classifier, separating hyperplane, and labeled training data. So what is a discriminative classifier? And so essentially what this means is that given all of the training data, it takes those elements all in as an input, and then it can separate and classify those elements to represent their specific feature set. And when we get into the case study, this is going to make even more sense because the entire point of the SVM algorithm is to be able to separate all the elements and then classify them so we can tell one class from another. Now let's go into the next definition, which is separating hyperplanes. And what this represents is a boundary that separates classes. Now this is very different than all of the other algorithms that we've looked at, and it's even different than pretty much everything we're going to look at in the future. And that is because with this type of setup, with this type of algorithm, the way an SVM works is it creates visual boundaries that separate the classes. And so what we can do with a hyperplane is it creates a relatively easy to understand visual for how a separation of classes is concerned. So when we talked about naive Bayes is very focused on being able to classify text into one category or another category. Well, with the way that an SVM works is it actually can look at all of the data points that you have inside of your system, whether it's a database, text files, anything like that, and it builds its own set of classifications. And as you're going to see that with this hyperplane, it actually creates boundaries where you can see that one type of data should be matched up and another type of data should have its own class. And that's the reason why you would use an SVM, is when you want a very clear distinction on one type of data versus another. And I know that simply looking at this type of dissection of this word and being able to understand it can be pretty challenging if you've never heard it before. And so once we get in the case study, this will also make more sense. But I want to introduce these key words to you so that when you hear me say them, they're not going to sound foreign. Now, the last element we're going to look at is labeled training data. Now, thankfully, this is one of the easier elements to understand out of everything else we've discussed so far, but I wanted to bring it up because labeled training data is one of the key prerequisites to the supervised learning set of algorithms. The main difference that you're going to see between a supervised algorithm versus a unsupervised algorithm is that supervised systems use labeled training data. And what that means is just as it says. It's required by supervised learning algorithms, which means that we know the names of the data classes. So if you're using an algorithm that is unsupervised, which we will get into later on in the course, we don't know what kind of data we're working with. Whereas with all of the algorithms inside of this category of supervised learning algorithms, it means we actually know what the data represents. So it's very similar to, say, that if you were working with Excel spreadsheets or something where you have columns that describe each one of the data points, you can categorize it that way. And so any supervised learning algorithm is going to fall into that category. So now that we've looked into the definition and we've also ripped apart a few of the definitions, now let's also take a look at the use cases. So when would you want to use an SVM? Well, SVMs are very good at image recognition. They're fantastic at handwriting recognition. They're very good at stock market predictions, and they're great with medical diagnosis tools. And so there are a number of other types of situations where an SVM works. However, these should give you a little bit of an idea of when you'd want to use one. And in fact, our main case study is going to deal with handwriting recognition. So now that we've talked about a few of the common use cases, what are some of the pros and cons to a support vector machine? Well, first, some of the pros. There is a very clear separation of classes. This is a great tool whenever you have a set of data points that you want to see a very clear delineation of one type of data set versus another. And once we get into the visuals, I think this is going to be very clear. I don't think there is any set of machine learning algorithms that gives as clear of a distinction between classes as an SVM. Another great rationale for using an SVM is that the predictions from this type of shallow learning algorithm can sometimes rival those of neural networks. And that may not seem like a big deal, but if you are in industry and you have started to build out these types of algorithm implementations, you will know that an SVM can perform in a few seconds what a neural network may take a few minutes, days, or even weeks to build out. And so there are many times where a support vector machine can be a fantastic choice. Even though it's much more simplistic than a neural network, it actually has some pretty impressive performance statistics. It also has a number of advanced options. We're going to talk about those a little bit as we get through the case study. Just know that the case study we're going to go through and the examples we're going to discuss don't even touch the full breadth of everything that an SVM offers, but I will give you an idea of what that looks like. And when we get into much later on in the course, when we get into the code implementations, then you're going to see exactly all of the cool things you can do with an SVM. Now, another great tool about support vector machines is that they work great with small sets of data. Very much like the naive Bayes algorithm, a SVM can take in a very limited data set and give you a great recommendation. So far, so good. Those are all of the great reasons why you'd want to use a SVM. Now let's look at a few of the cons. One of the first is that it can be a little bit challenging to implement. Obviously, we're not going to get into that too soon, but I will give you a preview on why an SVM can be a little bit difficult. And also, in addition to that, it also usually requires quite a bit of data pre-processing. And what that means is that whenever you're implementing a support vector machine, you have to have a pretty good set of quality data. Whereas with a number of other algorithms, such as the naive Bayes algorithm, where you can pretty much throw all kinds of data to it. So with naive Bayes, you could throw a million different HTML websites to it, and it could tear apart that data and give you a pretty good prediction on a category of content. A support vector machine is much different. With a SVM, you need to be much better and much more focused with how you parse your data so that you're giving it something that it understands how it should be working with. And so that is something to keep in mind. You're probably going to have to spend a decent amount of time before you even pass your data to this algorithm in making sure your data is organized properly. And lastly, on the con list, this is going to look a little bit confusing, and that is that there are multiple kernel options. So what in the world is a kernel option? Well, that is a great question, and it is one of the most important components in understanding a real-world support vector machine implementation. We're going to get into what it actually looks like, but to give you a high-level preview, the way a kernel option works, and it's also called a kernel trick, is that it gives you a different way to look at the data. It gives you several different ways if you want to think of it in dimensional terms. Imagine that you're looking at data in a linear sense, where it's just a flat set of values, where you have an X and Y axis. That's one way of looking at data, and many machine learning algorithms just do that. Well, with a support vector machine, you actually have the ability to add multiple dimensions. So you can look at data in a 3D or even a 4D or even more set of dimensional kind of perspective. And so that, as great as that is, it also adds complexity. And so we're going to have to see what that looks like, and then you can decide if it fits your scenario or not. So far, we've taken a very high-level overview of the algorithm. We've talked about the pros and cons and use cases. Now let's dive into our case study, and we have a pretty fun one. In this guide, we're going to talk about a handwriting recognition engine and how a support vector machine can be utilized in order to build it. So as you may or may not know, whenever you write a letter, when you use your handwriting to write out that address, you are not writing for a human to read it, but instead, the U.S. Postal Service has a set of algorithms and different robots that go through and read exactly what you've written, and they actually interpret all of this data, and they use tools such as support vector machines in order to be able to understand, as in this example right here, exactly the address that you wrote down to make sure it gets sent to the right recipient. And so how does this work exactly? We're not going to look at every element inside of the address. Instead, I simply want to take one specific one because this is the way the process works. It's not going to look at the entire address and build out a digital version of it all at one time. Instead, it's going to dissect it, and it's going to look at every element individually, and then from there, it is going to transfer it. And so right here, looking at our trusty machine learning funnel, it is going to take each one of the items that you wrote down. Let's take, for example, our handwritten 9. This is going to be passed through our funnel, which in this case is the support vector machine. And then the output of this is going to be a digital 9. It is going to be a 9 that the computer system that the Postal Service actually understands. So what exactly is going on in this funnel? Well, let's look inside of it, and we're going to see that there are a number of processes. The first thing that it does is it converts that 9 into pixels. And we're going to look and see what that actually means. But essentially what it does is it creates a picture of that 9, and then it creates a number of very small little boxes so that it can understand if there is handwriting in one of the boxes or if there isn't. And based off of those values, it is going to be able to generate its recommendation. That is where the data for any type of image recognition system resides. So that's the first process. After that, it is going to take all of the historical data, and it's going to separate it into classes. It's going to say these are all of the ones, here are all the nines, here are all the fives, here are the letter A's, and it's going to put those into classes so that we can create this classification and know if every one of the elements, where it fits into our system. So that's the second step. And the third one is it's going to compare the knowledge base. It's going to compare all that historical data with our new input. So it's going to take all the pixel data, and as you can see right here, when we zoom in to that 9, the way it works is every single element gets turned into this little tiny square. And in this case, I'm using color just to make it more clear, but the way the system is going to treat it is each one of these little boxes you see are going to be represented by a 1 or a 0. And this is going very low level. We're talking about being able to take this 9 and turn it into binary pixel data. So after the system has analyzed this entire number and it said, okay, in block 1 there is nothing, so this is a 0, and block 2 is the same, and it goes all the way through, and every time that it recognizes that there is some handwriting, it throws a little flag and says, you know what, this is a 1. This means there is handwriting in this section. What that does is it creates a digital representation of this number. And what that is going to do is that's going to give us real data that we can use to see how does this number, or whatever this is, it could be a letter or number or anything that someone wrote down, how does this compare to all of the other letters and numbers that we have in our system? Because that's how we're going to generate our recommendation on what this number is. So let's put this on a graph, because using our graph data and being able to implement our hyperplanes, like I told you, we're going to see exactly a visual format for how hyperplanes work. This is the easiest way to understand how the entire process operates. So we're going to separate the data into hyperplanes just like this. Now, I'm not showing you the finished product. What a hyperplane does is it separates one class of data from another. And so say that you have all of these different data points for all of the ones that we have in the database. So the U.S. Postal Service, every time they get a letter, they keep track of, okay, this is what a 1 looks like here, and this is what a 9 looks like. And they have all of this pixel data in their database. Well, there's a clear separation between the 1s and the 9s. But what we have to do with our support vector machine is figure out where that separation occurs. So each one of these lines, the blue, the purple, and the orangish yellow one, each one of these represents a potential hyperplane for our support vector machine. However, not all hyperplanes are created equal, and we're going to see that as we walk through and we try to pick out exactly what the best one is. So let's look at the blue one first. If we say that we choose this blue line as the hyperplane, which means that we're picking out this blue line and we're saying this is what separates the 1 from the 9, this may not be the best choice. Notice how our question mark right here, this represents a potential number. We don't know what the number is. It's simply our binary data that came in, and we need our system to estimate if it's a 1 or a 9. Well, right here, imagine that the hyperplane isn't there and you're simply looking at the data. This looks like a 1. However, because we chose our hyperplane to be where it's at, this would be categorized as a 9. Now, this is probably not the case because, as we can clearly see, the data looks like this question mark should be in the 1 category, but if we draw our line where the blue line is right here, that is probably not accurate. So what if we look at that yellowish type line? Well, right here we can see another example where we're placing a recommendation option inside of the 9 category when it's pretty clear that this should be in the list of ones. And so this is also probably not the best example. But now let's look at that third example where we have a purple hyperplane and we have the line drawn exactly where we have it right now. When we place this question mark here, we can see that it is falling inside the correct classification. And if we move it down, we can see that it is still working. So this is at an incredibly high level how a support vector machine works. Essentially what we're doing is we are trying to classify data by segmenting our data into as wide of a space as possible. So the language I typically like to use is I like to say that the widest lane wins. Now, lane is not the formal term. Instead, the formal term is actually margin. And so if we look at our lanes or our margins for all 3 of our potential hyperplanes, you can see right here that the purple lane is much wider. This margin here is separating our classes between 1 and 9 in a much better fashion than the blue or those yellow lines. And the reason for that is because the margin is the widest here. That's the reason why when we integrated those test questions, so when we put in our test data points, we saw how whenever we use that blue line, that it made some poor recommendations, and the same thing on the orange side. But you can see if we use the purple line as a hyperplane, this is going to give us our best segmentation and our best classification. Another formal term inside of a support vector machine is the distance. So what we say is that we have a distance 1 and a distance 2. Distance 1 is anything to one side of the hyperplane all the way until we find that first vector, and distance 2 is anything on the other side. So right here, as you can see, distance 1 goes from the hyperplane all the way to our first one. Distance 2 goes from the hyperplane all the way to that very first 9 that it found. Now, if you're wondering where the support vector name comes in, the vector is exactly the first element that our hyperplane finds when it's trying to build that margin. And that's a reason why they're called support vectors. And I think it's actually a nice name. It's something that is relatively straightforward to remember if you think about support vectors as supporting the margin. That's the way I like to think of it. That's how I personally remember it, is because a support vector is the very first element that the margin hits. And I think of it as a lane, and so I think of it as the support vector is supporting that lane. So now that we've talked about that, let's give a very brief summary on the key terms. We've talked about hyperplanes. Hyperplanes are the actual boundary between classes. We've talked about margins. Margins are the space between a hyperplane and the first vector, which is the first data point. The distance is each side of the margin. So every support vector machine should have at least 2 distances, one on one side of the hyperplane, one on the other side. And then lastly, we have our support vectors. These are the first data elements that give a very clear boundary on when one class starts and another one starts. So that's the basic usage. Now let's get into the advanced use of a support vector machine. First and foremost, we have multiple dimensions. Now you may have noticed when we looked at our 1s and 9s, you may have noticed that those are a very small segment of all of the data points that a system such as a handwriting recognition system would need to be able to process. And so it is possible in a support vector machine to have multiple dimensions. So we can look at ones and nines and letters and all of those kinds of data elements. And we're going to take a visual look at what that represents. Also, C parameters. As much as I would love to tell you that every support vector machine that you build is going to be perfect, where you have a very clear set of classes, that is not the case. There is going to be some overflow. In the example that we gave, there's going to be some ones that fit in the nines category and some nines that fit inside of that one category, and that is simply how the real world works. There's going to be certain people who write their ones very similar to their nines, and there's no way of having an absolutely perfect system. So a C parameter allows us to clear that off, and so we can ignore those type of data points. We also are going to have multiple classes. This is similar to multiple dimensions, but you're going to see that this gives us the ability to actually have multiple data points and analyze those all at one time. And then lastly, we have a kernel trick. Now, the kernel trick is something I already discussed earlier in this guide, but I'm going to give you some cool visuals so you can understand exactly what that represents. And it's very closely aligned with multiple dimensions. So as you can see right here, what we have is another graph, but this one is much different. And this is, like I mentioned, this is related to the kernel trick. We don't always have this really nice, clear, linear line, but instead, we also have situations where you need to actually draw a line that pulls off of multiple dimensions. And so because of that, a support vector machine is very popular for not just using a straight flat graph. It also uses a 3D graph, kind of like we have right here, where you can create a visual that takes in all kinds of different parameters, and then it builds its recommendation off of that. As you can see in this example, that gray line is very similar to the purple hyperplane line we drew earlier. And by leveraging multiple dimensions, we're able to slide our hyperplane across all kinds of different parameters so that it gives a clear distinction, not just between a set of a 1 and a set of a 9, but off of all kinds of different parameters. And that is a perfect lead-in to this next kind of advanced use, which is multiple classes. Whenever you see a support vector machine that performs more than binary classification. And when you hear me say binary classification, and I've said it a few times in this course, what that means is we have one answer or we have one other answer. But that is not always the case. That would make life very easy for us, but that is not always the way it works. Instead, there are going to be times where you need to be able to perform multiple classification, and this is when you're using a support vector machine. It's a great tool because you can do it. So right here, as you can see, we have hyperplanes that segment our 9s, our 1s, and our 5s. And last on the list of advanced usage is our kernel trick. Now, if you think that our multiple dimension description and our kernel trick are similar, they are. It really comes down to creating a different perspective on how the algorithm works. So here on the left-hand side, imagine that you have all of these data points. So in there, you can see we have all these little red dots, and inside of those red dots, we have all these blue dots. Well, you can't really create a circle that separates them, so our hyperplane can't really be a circle. But then with this kernel trick, the way it works is it converts it into what you see on the right-hand side, where you've actually elevated and you've added these other dimensions to the red dots and the blue dots, and now you can see there is a very clear hyperplane separating them. And so if you have a system that has multiple data points and multiple dimensions, the kernel trick is a very popular way to create a hyperplane that creates those kinds of classes. And thankfully, whenever you're implementing one of the popular machine learning algorithms, whether it be in Python or R or the language of your choice, whenever you call for a support vector machine class and you're passing the data to it, you can simply pass in the type of kernel trick and name that you want to use. And when we get into the code portion of the course, I'll show you exactly how you can do that, because each one of the kernel tricks functions a little bit differently. And the purpose of this guide is to give you a very high-level view to understand that a support vector machine focuses on classification, on recognition, and on creating a very clear boundary between different classes of data.